Forgot that.
Yeah, it does end up being one of those sort of first world problems in the end. So the preamble does take you perhaps frustratingly through that system of figuring out using elimination or substitution the values of S and T and substituting them back into the original equation to figure out what X, Y, and Z are. And you may have noticed, so the preamble doesn't cover it. The CMC lesson does go over kind of the idea, but sometimes you can get a value, you'll get a value for X and Y, or you could, if you wanted, you could get a value for Y and Z.
Yeah, I was wondering if you could do that.
Yes, and so in the preamble, it actually shows, deliberately, it shows these two lines and they're intersecting at something like 3 and 2 and 2 or 3, 2 and 3. And you're looking straight down the Z-axis onto the XY plane. And I saw that you noticed, that you rotate that, and you'll notice that they do not, in fact, intersect. In 3 dimensions, they're known as skew lines because they aren't parallel, they aren't coincident, and they don't intersect. But if you're just looking at the X and Y values, it does intersect. It intersects at 3 and 2. And so you can do all the algebra. You can come up with an X and Y value of 3 and 2. And you have to make sure that it's consistent for both S and T and you have to make sure that you get the same Z value.
Exactly. If the
for those values of S and T.
The lines are really crossed, yeah.
Yeah, or else it's a skew line. So you have to go and double check your work when you're working in this third dimension, because you can pick up the 2-dimensional intersection and miss the fact that they do not intersect in 3 dimensions.
Yep.
All right. So the second technique that they use in the CMC lesson for finding intersections of lines, it's not that different a game, but it's a different step than the substitution or elimination that was our best friend back in grade 10. And what they actually do is they develop the parametric equation from this vector equation, and then they substitute the substitute it in for X, Y, and Z and start to solve it that way. So I'll just go over that. And then we'll talk a little bit about consistent and inconsistent systems. And so X, Y, and Z is equal to 3, 1, negative 1 plus T times the direction vector 2, 1, negative 3. And so I can turn this into the parametric equation, 3 plus 2T, and Y equals 1 plus T, as long as I haven't made a mistake yet. Nope. And Z is equal to negative 1 minus 3T. Okay. So we have a wealth of equations and not so many unknowns. And so this second technique involves taking these expressions for X, Y, and Z that are just in that one variable T and substituting them up into the symmetric equation. And you're going to do it 2 at a time, and then you're going to check your answer using the third equation. And so X is equal to 3 plus 2T. So where I saw an X, I'm going to put in a 3 plus 2T. And my Y is 1 plus T. And so where I saw my Y, I'm going to put in a 1 plus T. And now I'm going to isolate the T. So I'm going to cross multiply here. I'm going to simplify the inside. 2T minus 4 is equal to 2. And this is T minus 1. And simplify. And I'm going to isolate T. So I'm going to move it over onto this side because I happen to dislike negatives because I tend not to write them again. They magically become positive.
Yep.
So when it all comes down to it, I get 9/5 for t. Yeah, I think it's right. Okay, I can go merrily along thinking, yes, 9/5 t, that's good, but I also have to make sure that this is going to be consistent if I plug it into these two, okay? And so this is the second part. In order to check that out, I'm going to plug in y and z, the parametric version, into the symmetric over there. Okay. So y is 1 plus t minus 2 over -4. And if I do the substitution for z, -1 minus 3t minus 17 over 5. So this is t minus 1 over -4. And this is -3t minus 18 over 5. Now I'm all ready to do my cross multiplication. Just keeping an eye on my old t here. 5t minus 5 is equal to 12t plus 4 times 48. 72? 40 plus 32, 72. I think that's right. Okay, so I'm going to move my t's over onto the right side. 7t is equal to -79. Wow. And so I'm getting a different t value, as long as I didn't make any mistakes. And actually, I don't think I did. But the answer is that these two lines do not intersect.
Okay.
And they do go over a final technique in the CEMC exercises, which is you derive a value for t, you get your x and y and z coordinates from one equation, and then you see if you get the same coordinates out of the other equation. So it's a second way to test. Make sure your x and y's and z's are all the same.
Mm-hmm.
So that's it. I guess we should talk about inconsistent systems for a minute.
Okay.
Because they do just talk about the different situations. So if you're in two space, there are three possible organizations for the lines. So if I have two lines, what's one possible way these lines could be organized relative to each other?
Parallel.
They could be parallel, that's right. Okay, there is no solution to this system, so it's inconsistent. There are no common points. And so when we go to solve this one, we're going to get like weird answers. We'll get 0 x equals 5, which just can't be. So that we would say that's inconsistent, that when we go to solve that system, and it means they don't intersect. Okay. And the second very common thing in two space would be
Perpendicular.
If you just said intersection, and I think I have my speakers turned down a little bit.
I said
yeah.
perpendicular, but I guess
this is that's pretty common in two space. So those two lines are going to intersect. We're going to solve that system, and we're going to come up with a value for x and a value for y. And that point is going to lie on both lines. And the last possible organization 2 space is that situation where they call the lines coincident. And so really it just means, you know, they're the same line. This system is still consistent. You're going to wind up with solutions that look like 0x equals 0. And that's true for any value of x, always true, 100% of the time. And so any point on the first line will also satisfy the definition of the second line.
Okay.
Then 3 space, we get into that final possible level of organization, which is the pair of skew lines. And in 3 space, most of the time, those lines are going to be skew if it's just random. If you're making up algebra problems, though, they tend to intersect, so you don't have to worry too much about that. But the last one are the skew lines, and we had an example of that just in the preamble there. They don't intersect, they're not parallel, and they're not the same. And those are the cases where, yeah, 2 of the coordinates will work together, but then when you go to find out what the third one is, it just won't work. It won't work with the first 2.
One of the coordinates is not the same. Then.
Sorry, what was that?
Yeah, one of the coordinates is not equal to the other.
Yes, that's right. Yeah, so you might get an x and y and a z value, and you think, good, I know where this point is, but then when you go look at the x and y and z value, one of them won't match up.
Yes.
So, yeah.
Okay.
All right, good. Any questions?
No, everything's been pretty straightforward with this lesson, or this unit really so far, so that's good.
Yeah, this unit's it's pretty nice. The next unit gets interesting just because we start looking at planes and organization of planes. The next lesson we pull an interesting trick, which is finding the distance from a line to a point. And in order to find the distance, we mean the shortest distance. And so we're always talking about the perpendicular distance between a line and a point. So we need to use the normal vector for that. There's nothing normal about that vector, let me tell you.
Oh no.
All right, look, it's sunny out. Did you know it's sunny out?
It is.
Yeah. The weather, I feel the weather forecast changing for Friday already.
Let's hope it stays pretty sunny.
Yeah, they're sure being pessimistic, but
We'll see.
anyway. All right, let me know if you've got any problems.
Yeah, I will.
And we'll be done this little subunit tomorrow.
Oh, perfect.
All right. How many days left? 7. Lindsay says
Yep.
7.
7 after this.
7 after this. Yep.
Good stuff.
Okay. Thanks, Jeff.
Yeah, thanks a lot.
We'll see you tomorrow.
Yeah, see you then.